Hi everyone. Today we are going to discuss about some applications of pigeon call principle. And in simple words, pigeon call principle states that if there are young pigeon calls, and young pigeons run into this young pigeon calls, and if m is greater than n, there are more pigeons than the pigeon calls, then at least one pigeon call will occupied by more than one pigeon. That's the concept. Or more mathematically, more generally, if there are n elements which is distributed into m different sets in such a way that n is equal to some k into m say plus 1, then at least one set will contain k plus 1 elements. Or in other ways, if say, can realize it this way, if you have n elements, m elements distributed among m categories or sets, and then at least one set should contain k plus 1 is equal to n by m, the seeding function, n by m elements. That means the number of elements in at least one set is the greatest integer, which is greater than n by m. So this is the most general form of pigeon call principle. And in simple words, if we have more pigeons than the pigeon call, then at least one pigeon call is occupied with more than one pigeons. Now let us go through some simple problems. So here first one, if I have 12 pairs of socks, each pair a different color in a bag, and how many socks I have to draw at least from the bag randomly to get a matched pair. So it's not a question of probability. This randomly does not imply any probabilistic method here. So here we have 12 different colors of socks of 12 different colors, and we are mix that 12 pairs, that is 24 socks, in a bag, and draw socks randomly from that bag one by one. And let us consider the 12 different colors as pigeon calls. So this number of pigeon calls is 12. Now I'm randomly drawing socks from this bag, and to ensure that at least one cell corresponding to a color contains more than one socks or pigeons. So here the term pigeon stands for a particular color of socks, say something like red socks or something like that. So to ensure that at least one color occur twice, we need more than 12 socks. We should select more than 12 socks. And the next number greater than 12 is 13. So we need 13 socks to ensure that we got a pair. So as it is, the selection is random, we may end up with a paired socks before we choose 13 socks. That is possible. But if we are selecting socks from this particular bag in a dark room, and we are required to take the minimum number of socks in such a way that we can ensure there is a um, pair of matched pair in our hand, then the minimum number or minimum required number of salts we should take with us is 13. And now, second one, if there are 8 people in a room, if there are 8 people in a room, at least 2 of them have birthdays that occur on the same day of the week. So here we consider the pigeon hall as the days 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, 7 days in a week. So number of pigeon halls is equal to 7. So pigeon hall is 7. And it is given that there are 8 persons in the room. So 8 is greater than 7. So by pigeonhole principle, it is guaranteed that at least one of these 7 pigeonholes or 7 days is occupied by 2 persons. So at least 2 persons have the same birthdays. So that is how we use pigeonhole principles directly into problems. So there is another one. An auditorium has a seating capacity of 800. How many seats must be occupied to guarantee that at least 2 people seated in the auditorium have the same first and last initials? So the first initial, we are considering here the letters from English alphabet. So the first initial can be any one of these 26 letters, and the second initial also can be any of these 26 letters. So we can have a total of 26 into 26 different uh, possibilities for the first and last initials of the persons. So, uh, so the different possibilities of initials is 26 into 26, that is 676. Now, to ensure that there is at least 2 persons with the same initials, so let us consider the pigeonholes as the different initials. That is, there are 676 initials, and they are the pigeonholes. 676 pigeonholes are there. And to ensure that there is at least one cell with more than one person, or at least one initial which is associated with more than one person, we need 676 plus 1 is equal to 677 people accommodated into the auditorium or seated in the auditorium. So that is the minimum required number of people in the auditorium to ensure that at least 2 of them have the same set of initials. Now, the fourth one is let us consider ABCD a square with A into B is equal to 1. So it's a square, which means 4 sides are of equal length, and A into B is equal to 1 means A is 1 unit and B is 1 unit. And show that if we select 5 points in the interior of the square randomly or in any way, there are at least 2 points whose distance apart is less than 1 by square root of 2. So here, first step, we just find the midpoints of each side and divide the square into 4 equal parts. So let the square be AB, C, sorry, C, D, A, B, C, D. Then the uh, midpoints can be named as E, F, G, H. Then the center point can be named as some I. Now, here we get four regions. We can name them as R1, R2, R3, R4. They are similar to each other. And observe one more thing. Okay, when we define the region R1, we can include the boundary EI and exclude this HI. And in the second case, we can define, say, the points on IE into R2 and exclude the points on R3 and so on to eradicate the confusion about the points on the boundary. Just include one boundary points into R1 and other one some boundary in R2 and R3 and so on. We can define R1, R2, R3 and R4 in such way. And now, by pigeonhole principle, just consider this R1, R2, R3 and R4 as 4 pigeonholes, and we have 5 points. We choose 5 points, and 5 is greater than 4. So there is at least one pigeonhole, that is R1, R2, R3 and R4, which is occupied by 2 points. So one of these four regions will contain 2 points. Now, if you closely examine one of this particular square, then its dimensions are this is 1 by 2, this is 1 by 2, so this diagonal distance is 1 by 2 the square plus 1 by 2 the square, that is equal to 1 by 4 plus 1 by 4, that is 2 by 4, that is 1 by 2, and therefore the distance of this diagonal is square root of 1 by 2, that is 1 by square root of 1 by 2 or 1 by root 2. The maximum distance possible inside this square is 1 by root 2, and if we have at least one square in which we have 2 points and the distance between those 2 points is less than 1 by root. So we divide the total region into 4 equal right angles or similar right angles. Then by pigeonhole principle, we can ensure that at least one of this region is occupied by 2 points, and the maximum distance in or the diagonal distance of subregion is 1 by root 2, and therefore there exists at least 2 points for which the distance between them is less than 1 by root 2. So these are some applications of pigeonhole principle, and this is very interesting to use pigeonhole principle. So we'll go through more problems on pigeonhole principles, and thank you.